by, what you usually start. You just start coding without any plan. And then a couple of weeks passed, and I realized I had to step back, try to process some of the thoughts and experiences from that, and try to coalesce into something presentable. Right. Just some legal things first, or a disclaimer. So as I said, this represents some current thinking here. So this is not, anything like proven or anything like this. It's current thinking, and by current thinking I mean some of my experiences. Of course, all inspiration from talking with Victor of the subject, and talking with other team members of the subject, recent discussions with status on the subject, etc., and so forth and so forth. A couple of other things. I'm not going to talk about how you encrypt things or anything like this. So the idea is to try to create a layer that's crypto agnostic in a sense. It does rely on the privacy guarantees that Swarm has generally. I'm not going to talk about insurance and persistence. I'm not going to talk about identity discovery, so how do you find out what key represents a real person or anything like this. It's just kind of current thinking, hand-wavy stuff, and yeah. So just to make it clear, we are not sure. It's just some current thinking, yeah? So I don't really have to show this because Javier just went through this. But what are feeds? So basically it's have one persistent identifier that's always the same to point to data that has identifiers that's always changing. So on the right side we have swarm hashes representing different updates of data. On the left side we have the feed. The feed then comprises of short explanation, some key that's signing the feed, and some topic that's an arbitrary 32-byte entity. So the basic building block of creating a chat, and the most obvious thing that comes to mind, is to create a linked list of Swarm updates. So basically, the top one points to the next one, points to the next one, and so forth. And then you use feeds to create the lookup point of the most recent one. You find the recent one, and you just follow the linked list down. So, I'm going to separate into one-to-one chats and multi-user chats. So this is an example of a one-to-one chat. What we see here is that the first update they have, they initialize the chat on each side, and then they post some messages, some update to the chat on each of their feeds, respective feeds. Now the feeds have, for A, he signs with his key, A, of course, but the topic of the feed is B, key B, or some function of key B. And B does the same thing using the topic for A as, the key for A as the topic. Since we assume, for the moment at least, that they know each other's keys, that's a predictable scheme of finding out how you can build a chat between two people. Clear so far? Good, okay, cool. So what they then do is they pull each other's feeds for updates, and using the timestamps on the messages, they can merge these two feeds into time stream of messages that represents the chat in temporal space. Group chats are pretty much the same thing. Although, so the basic principle is the same. Each participant keeps one feed with their individual updates. Each participant in the feed merges all those feeds each participant in the chat merges all those feeds into a single stream of updates on their respective clients, but the topic here is different. They sign the feed with their own key, of course, but the topic of the feed is the room name or some function of the room name, for example. So how do they know who is actually in this room? To each message, so let's assume that each of them keeps a list of all the participants in the room. And then for every message that they post, at the time of the message was posted, they include a hash to that participant list in the message. So now we can follow. In temporal space who joins when and who were the recipients for the different messages as time goes on. So here, for example, we have A, B, and C being in the chat room. Initially, they are linking all the messages to participant list with A, B, C. And then Mr. Creosote over here joins a little bit later. And when he joins, then the participant list is updated, and all the following messages are linked with that new participant list, with the 4 participants. So how does this joining somebody new work? Or, I mean, how can it work? I'm not going to make any bold claims. So let's say A over here is the responsible party in the group to add D to the chat, or Mr. Creosote. Then he could issue, for example, an update, which is a system update, saying, I want to move this chat to participant list 2. And then you see D and A initialize a new feed on this participant list 2. It's basically the same room with the same topic, right? But the future messages will now be linked to the new participant list. The other guys could agree on this. They issue their own move to participant 2 order and create an initialize update of their own. In which case, everything is hunky-dory. Actually, this is, kind of a forking of the room in a sense, right? You can even make the forking even stronger by including the hash of the participant list in the topic of the room itself. Then it's very clear. It's not even going to be the same feed. They can, of course, reject it and say, nope, forget it. I don't want this guy to join. In which case, Creosote is understandably disappointed, and A would return back to the original chat. Or perhaps they just don't say anything, implicitly timeout, and then because the chat times out, then they just assume that they don't want to add him. So, as I said, the responsible party for joining would be B in this example. So, how will this protocol work? Well, then A would ask B, what is the participant list of this room? B would answer BCD, for example, is the participant list. And now he knows about C and D. So he could check with C and he could check with D, of course, and see if they match with each other. If they do, then it's hunky-dory. If they don't, well, at least the majority might be right in this case, so maybe he wants to trust the majority. If the majority screws him over, of course, he's understandably enttäuscht. Was it disappointed? Thank you again. Solving this consensus issue is not going to be a part of. So it's not within the scope of this talk, but let's say there is some algorithm that, or it would, if we push that to the application level, for example, how to resolve these kind of consensus conflicts, and hope that peace will ensue. So to recap a little bit, for single user chats, A needs to keep one feed to each of the participants, B, C, D. That means A signs the feeds, and the topic is a function of their key. And he needs to pull a feed from each of these participants where the topic is a function of his own public key. For multi-user chats, it's a little different then. A would only keep one feed for his updates to the room, which are read by B, C, and D, the same feed, but he has to pull and follow the feeds from B, C, and D. Is that clear so far?
You can achieve a one-to-one with the many-to-many. So is there an overhead in the many-to-many that you might choose the one-to-one as?
You could, sorry, what was the question?
Chat can be limited down to one-on-one chat, right?
Mm-hmm.
The stuff on the right. In theory, the stuff on the right could be used for just one-on-one.
Yeah, so it's kind of the same as this, right? But here the topic is the room, right? Yeah.
So is there any reason to prefer to use the stuff on the left if the stuff on the right is capable of the stuff on the left?
Prior play is that if you have group chat, if you want to do a one-on-one, you can consider this a group object you run in your department. So you can ignore like.
Oh, you can ignore this at all. Is that what you mean? Ah, I see. Yeah, yeah.
So is there an overhead where you might?
Oh, yeah. So the only reason is that in this case you do not including the participant list. So
Very small overhead.
it is a very small overhead. So yeah, basically you could do the same thing. So it's just that in this case you don't really need it. So that hash you wouldn't include it in the message maybe or something like that. But yeah, totally flexible. Sorry, I didn't understand the question at first. Yeah. So. I started kind of in the middle of the story of how to describe the interchange of the messages themselves, like when you're at it, but how do you discover each other in the first place is the question. Now, I said that I was not going to talk about how to map real-world identities human identities to real-world key identities. But for the purpose of this talk, we will assume that there is some public identifier key that A can know about if he wants to get in touch with B. So phone book or whatever, right? So that would be, this is of course, enclosed to the world and everything. A, on the other hand, would create a totally random key from lots of entropy. So the idea is that A needs to transmit this key to B somehow. Well, how can we do this? Well, there can be a contract, of course, on the blockchain where B listens for submissions to somebody wants to get in touch with you method call. We can actually use PSS for this. One example, either in the phone book, B can enclose the address and the key of the node that he's connected to receive this PSS message, or we could imagine that the PSS message is sent with fuzzy addressing, or even as a broadcast, message, kind of like a whisper message. You can, of course, go the old school way and do a USB stick or telegraph or something like that. That's always an option. A low security idea that I had the other day is to use a reverse feed in which you do a big no-no of creating your public key. B creates his public key, but also a temporary private key called btemp, which, I think I screwed up the letters here, which A then can use to create one update in that temporary feed, which contains the key, his randomly generated key. That, of course, can also be encrypted with B's key, so nobody would see that key. But obviously this is not particularly secure. But let's step back a little bit and think about secure. What does it mean? Well, there are different FET models around. Like the world is, so it's a different story if NATO is out to get you than if you just want to dodge the big data AI harvesting of the FANG group, or if you just want to have a small band-aid for your security, right? But let's face it, that the threat that comes from NATO and NSA and all of these isn't really relevant for most of us in day-to-day life. I must say for my own part, I usually rent my apartment when I go away, and I did this time as well. I was emailing with the guy, and he wanted to have a copy of my passport, understandably, right? Because, yeah, some security when money changes hands. And he had a Gmail account, and I was figuring, well, I don't really want to send my passport to, or a copy of my passport to Google. Not that I don't want to give the AI the free scan of, you know what I mean, right? And I was thinking, well, what options do I really have here? Well, so we could do the PGP thing, of course, but then he wasn't tech, and actually tech people don't even do that because it's too complicated. And then, well, Telegram or WhatsApp, but then, it's the same kind of story, you're fucked in another way. And then somebody said Signal, but then you have the whole story with, well, he actually has to install this app, There's the active thing that he has to perform, and he has to tether it with the phone, and blah, blah, blah. So maybe somebody has a better idea. I was Googling Disposable Chat to see if there's, some way of actually doing this in a disposable way. There was, but they were all client-server based. So it's disposable but it's on the server, right, of some guy. So let's, just as a thought example, let's see if we can use that latter insecure thing to outline a disposable chat. So in this same manner here, A generates the public key randomly, generates this private disposable one-time update private key, and sends this to B. In my case, it would be I send him this in an email, right? At the same time, some code is generated that we put on Swarm. So basically what this looks like is that A would press a button and a link would come out. That link would point to some JavaScript code that, when run, will generate a key for B, which would be then fed to A using that temporary private key. I don't even know if I explained this very clearly, but in this manner, now using that disposable key, both of them have each their own public keys. The only thing that we really needed to exchange was this link to Swarm, and it happened magically. And that's a disposable chat. I could then send my passport, and that was it. So I was actually thinking about this would be even in the scope of the hackathon to do. So if there's enough time, maybe somebody will want to join with me to hack around with this. So back to this. So the key exchange thing. So we of course want to try to avoid outside entities seeing or deducing what our identities are based on our keys. Well, we want to keep our keys private, right? Or so one layer of the security is to hide the content. Another layer of the security is to hide who is actually talking to who and what kind of activity you have. And I mean, if they know your keys and they know that you belong to the keys, that's a no-brainer, right? But if they just see some keys and they don't really know who's behind them, but they can see what activity these keys have, they can try to match them up by saying, okay, well, when this guy has activity, and might be able to do something, so that might lead them to the IP address, which might lead them to the person, and that's, of course, a bad thing. So, how to thwart this? Well, in the initial case here, right, we had a random key of A, and we have a public key of B. The public key of B is known, it's like a global identity, so anybody knows that. So what is the first thing they do when they establish the chat? Well, B says, oh, B generates a random key, and says in this encrypted part of the chat that, well, let's move the chat to this pair of feeds using my new random key. And then A could, in the same old chat, say exactly the same thing, generate a new random key, and then he also moves to this pair of chat with that random key. Now, from the outside, of course, this communication is encrypted with their public keys, so the outside entity can't tell which address they move to. And that means that basically they could end up in any point of the address space that are occupied by feeds. So that's 20 bytes of user address. And theoretically, you could, for each and every update, you could even change this key if you wanted to, if you accept the overhead. And there's not necessarily that much overhead involved. If it's possible I don't think there's an API for this now, but if you can insert an update in the feed without doing any kind of lookup of, is there already an update in this feed, but just place it like in the slot where it belongs in time, then you could do this with quite not so much overhead. Right. So, speaking of overhead, there is overhead involved in polling these feeds all the time, especially if there's a lot of them. So, I mean, this is particularly a problem with smartphones, I would imagine. What you can do is agree on some sort of max poll time space, where you say, for a certain period of time, I don't know, 4 or 5 seconds or whatever, you would poll the other one if there was activity, but then after that you stop. And the contract is then that when he doesn't update again, he will notify you with a PSS message. And then you start polling again for the same amount of time. Of course, this also leads to certain privacy issues if you're worried about who's talking to who, because now, theoretically, it could be possible to correlate if there is a pause in your communication, and it starts again, and that generates a notification, and you can figure out where the PSS message ends, you can figure out the IP, and et cetera, and you're fucked again. Perhaps one way of doing this even a little bit more concealed is Victor's idea about mailboxing. So correct me if I got this wrong, Victor, but basically what A can do, A can create a secret which he shares with B, C, and D. And then he says that I want you guys can send a request to this mailbox node M to create an update which has the topic of this secret. So M doesn't know what this secret means. B would basically just send a message to M, give him some money, and say, can you please create an update with this topic and which points to, for example, my public key, or some identifier that A knows maps B's public key. What's the advantage of this? Well, for one, M doesn't really have any way of knowing that A is the audience here. So the recipient of this update is masked. The other advantage, of course, as we can see, that here A can pull the feed of this mailbox to see if there are, in fact, updates now from either B or C or D. So it solves the same problem of the PSS notifications, but without the perils of disclosing IP or location. Did I get it right, Vic? Kind of? Oh, great. Thumbs up. I think that was it. basically.